Welcome to the deep dive. Today we're digging into a really unconventional blueprint. It's for the Bar Spintronic quantum processor.
hmm
And this isn't just about making things faster. It represents a truly strategic shift in how we think about errors in quantum computing.
It really does.
The standard approach is all about defense.
Yeah.
Maximize coherence, minimize noise, and then clean up the mess later with error correction.
Right. Massive error correction codes post facto.
Exactly. But this new design, it says, no, let's treat that decoherence, that noise, as a controllable variable.
And what's so fascinating is that it's all rooted in information thermodynamics.
Okay, so what does that mean in practice?
That coupling term, the psi bar, it's basically a thermodynamic control loop. You're not just fighting entropy,
You're steering it.
you are actively steering it. The goal is to guide the von Neumann entropy, the quantum measure of disorder, to a constant optimal state. It's what we call dynamic dissipation engineering.
So if the old way is building a fortress, this is more like turning the enemy into a tool.
That's a great way to put it.
But how does this abstract field theory, psi and psi bar, actually map onto a physical silicon chip?
Okay, so the core of the processor, the psi field, that's physically the electron spin state inside these quantum dots.
And you're using a silicon germanium platform for that.
We are, yeah. It's a leading platform because the coherence times are just so long. It's a great starting point. But the real trick is psi bar. You can't just create an antiparticle in non-relativistic silicon.
Right, of course. So what's the workaround?
That's the elegant part. Psi bar is functionally mapped to a coupled degree of freedom that's already there. The valley state.
The Valley State. But isn't that notoriously noisy and difficult to control?
It is, and that's the whole point.
You're using the problem as the solution.
Precisely. The valley state becomes this ancillary quantum channel that mediates the interaction and the noise. It's the physical proxy, what we're calling the entropic adjoint. We're not minimizing its influence, we're incorporating it into the control loop.
That's a wild concept. And the silicon platform